Thanks, Frank. And Frank, of course, left out the fact that he was a co-author on that paper. I think he was maybe the first author on that paper.
That was Chris.
Yeah. Oh, he was second. Yeah. Okay. Uh, anyway, very happy to be here. So yeah, let me just dive into it. I'm going to tell you about algorithm configuration, but I'm going to talk about a kind of utilitarian perspective to algorithm configuration, and by the end, I'll tell you what that means. So. As always, the work that I'm going to describe today surveys work with a whole lot of different co-authors. Kind of depends on when you want to start counting. I'll be referencing even some of the old work with Frank and Holger and many of those co-authors. But these are the people that I've been working with most recently on this work, and particularly Devin Graham, my PhD student, is the sort of linchpin who put all this stuff together. So thanks, Devin. So let me dive in and talk about algorithm configuration. How many of you here work on algorithm configuration? Shame on the rest of you, but what can you do? How many of you here know what algorithm configuration is? It's kind of the same people. That's a bad sign for algorithm configuration. What are you going to do? So by the way, I really want to make this interactive. We've got an hour. So if you've got something to say, stick up your hand or just start yelling at me. Like rather than saving everything for the end, I think it'll be more fun if we make this kind of a discussion. I'm used to giving talks in economics departments and they just kind of go for it. So I kind of enjoy that sort of way of doing things. So let's see what happens.
Try to get them up. There's a signal in your meter or something.
Okay, fine. So if you just start yelling things, you have to yell them so loudly that the mic will pick you up, or you can just wait for the mic to come to you. That might be the classier approach. Okay, maybe we can get one of those two mics on the other side of the room. So I want to argue that, as many of you might know, some of the early AutoML systems and probably some of the AutoML systems people use today have used algorithm configuration methods as sort of optimizers within them. So AutoWeka actually had SMAC, which is an algorithm configuration method, whether you know it or not. That's what the AC stands for in SMAC, as its kind of optimizer that was used to perform AutoML. So there's this sort of superficial sense in which algorithm configuration and AutoML have been deeply connected to each other. But I want to argue that there's a more fundamental sense in which automated algorithm design, which is really the way I think of algorithm configuration, is an AutoML problem. So let me try to lay that out. And I think the way to do that is by contrasting the way machine learning used to be done with the way that it's being done today, and then to sort of see the parallels in algorithm design. So in machine learning, we used to, before all of you were born, think of building systems where we crafted features using expert insight. You would think very carefully about which things you wanted to measure about the problem. You would go to NeurIPS and find out which model family was the cool family that everyone was using that year, and you re-implement everything with support vector machines or whatever it was, and then you'd manually tune hyperparameters. Boo hiss. Now, in modern ML, we've moved to taking the human out of the loop on most of those steps. So we now have very highly parameterized models. We try to use expert knowledge in the construction of these models as little as possible. If at all, we want to use it maybe to identify the kinds of invariances and model biases that are important for our models. We make these models deep in the sense that they have many, many layers of nodes and just generally highly parameterized. We deal with the corresponding enormity of this problem by having huge amounts of data upon which to train them. And then, of course, optimizing a loss minimization problem in very high parameterized space on a lot of data is computationally intensive. And we deal with that problem by just biting the bullet and just paying the cost anyway. And that kind of has gotten us to where modern ML is today. In discrete optimization, so when I'm talking about optimization algorithms here, I'm not talking about convex optimization algorithms like gradient descent. I'm talking about NP-complete optimization problems like mixed integer programming or satisfiability or problems like that. So when we solve those kinds of problems, the classical approach looks a lot like classical ML, where an expert comes up with a bunch of heuristic ideas for their algorithm, again, based on some sorts of intuitions and insights. And they iteratively conduct small experiments where they try out different versions of their algorithm and see what happens to improve the design. And then, eventually you get to the IJCAI deadline or something, and you submit what you've got. I want to argue that the way you should approach automated algorithm design is looks more like modern ML, where you take very highly parameterized algorithms that express a huge design space of possible choices. These are deep in the sense of having many layers of parameters that each depend on the previous. This optimization problem is hard to solve, and so you need lots of data to characterize the distribution of interest. And you bite the bullet computationally and do huge search in the space. And so broadly speaking, this is machine learning, right? What you're trying to do is find some loss minimizing point in a hypothesis space that generalizes well to new examples and that fits a particular distribution of interest. And so this really is an AutoML problem. It isn't just sort of useful to AutoML. This is what AutoML is if your design space consists of algorithms rather than predictive models. Here's a graphic that Frank made back at the dawn of time. You can tell by the level of production quality here, but it still kind of tells the right story, right? So what this is trying to say is that algorithm configuration is a sort of meta algorithm in the sense that it's an algorithm that takes another algorithm as input. So it's an algorithm that takes some underlying solver as a kind of black box input, and then it runs that solver with different parameter settings, measures what happens, and forms beliefs over time about how that algorithm behaves. And so this is an instance of a kind of black box function optimization setting, but it's a special one where the black box is an algorithm that I'm going to run, and I'm able to stop the algorithm early. So often what I'm really going to care about is having the algorithm perform quickly. And I can infer from the fact that the algorithm is still running that it's taken too long and stop it. And that property where I care about time, and the longer things take, the worse they are for me, is going to be a really important ingredient of this setting that we'll be able to use a lot. I also want to notice here that algorithm configuration returns the solution cost. Ordinarily, in the literature, this has been the average runtime across all of the instances that we've evaluated, and that's where I'll start out. But that's something I'm going to return to midway through the talk. So in the interest of let's do it.
In a seminar, and just to like interrupt you, on the slide where you're talking about algorithm configuration and you're comparing it to AutoML, how should I think about mixed integer programming solvers that, like, I think of that as being it's a big heavy black box that arguably can solve any discrete optimization problem or any discrete optimization problem within reason, but it has more of like a theoretical, it tries to provide a provably optimal solution. Like, is that a heuristic algorithm, or like?
Well, I think it's somewhere in between. So I think if you take Cplex or Gurobi, if you really dig into the manual, they expose hundreds of parameters that don't affect solution quality, that only affect the performance of the solver. And many of these are sort of deeply conditional. Like some module gets turned on, and then it has its own parameters, and they might have subparameters. And the people who designed this thing don't themselves know how they work. I mean, I know because I've talked to them and worked with them actually a bit on this. They know something about it, obviously, but like in terms of what it's going to mean on its performance. And so really, you can think of this whole parameter space as inducing a model family, a parametric space of solvers, each of which is provably correct, but whose performance is very different. And within this space, my loss function is not, was my performance correct? Because it's going to be correct no matter where I am in the space. My loss function is how long is it going to take me to run this on my distribution of interest? So that's exactly the kind of picture I want you to have in your mind. Thanks.
Okay, awesome.
Somebody over here.
I'm going to support Peter's interest into making this like an economics talk. And actually in this comparison between machine learning and discrete optimization, For the comparison of machine learning, you said that in the old days, we would hand design a bunch of features, and that was sort of done by experts. And in modern ML, this is now done in a much more automated way using essentially representation learning.
Yep.
But I want to question one of the implications sort of that comes from this by pointing out that I think it's reasonable to say that this causes more time to be spent by humans on algorithms. Humans just aren't spending it on feature engineering. They're instead spending it on data set curation and creating the pipelines that are used to train the algorithms in the first place. So I'm just curious, if you buy that argument, sort of what the implications of it would be for the discrete optimization side.
Well, I think yeah, I mean, that was a long question. I'm not sure I can untangle all of the pieces of it, but I do think the goal here is not necessarily to reduce the amount of time humans are putting in, but it's to make the outputs better than they were before. I do think something we've learned is that data set curation is really important, trying to understand the target domain upon which you want to work well. And I think in optimization, there's no free lunch in optimization, right? Unless P is equal to NP, any algorithm is going to be bad on some inputs. And so, but we don't think that, there's a perfect computer vision system that can recognize anything. We only care about recognizing images from the world we're in. And so, you might similarly think that, I just want to find an optimization algorithm that performs well on the kinds of problems I actually have. So I think thinking about curation, thinking about coming up with a space of candidate points, which is to say sort of candidate algorithm configurations that performs well, that surfaces interesting points, all of this might take human effort and is I think worth that effort. But it's different from thinking that you have an intuition about what each of these ingredients is actually going to do, and I'm going to design the algorithm in a way that I understand. I think we're going to see a movement away from that.
Okay, thank you.
Cool. You've got something to say too? All right. No, just keep it away from them for a minute. This is slide one, much like an economic talk. There's this sinking feeling where you're like, I don't have a slide a minute, but I wasn't exactly expecting 15 minutes on the first slide. So we'll see what happens. Okay. But now I'm already on slide 3. So we're making progress. Okay. Yeah, so lots of people, around the sort of turn of the millennium, the first decade of the millennium, came up with algorithm configuration procedures that work well in practice. I'm not going to tell you great detail about all of them. I'll say a little bit about SMAC, but broadly speaking, they're all heuristics that seek to do well in this kind of black box world. Let me tell you a little bit about SMAC, which is graphically depicted here. So broadly speaking, what SMAC does is it learns a machine learning model from the performance data it has so far. It uses the model to select configurations that it thinks are worth examining. It then actually goes off and examines them. It actually does black box runs on these algorithms to see how they perform compared to the best thing it knows about so far. And then it just repeats this thing in a loop. And of course, initializes by doing some initial runs so the model has something to get started on. And so broadly speaking, SMAC is this sort of Bayesian optimization approach that is driven by a random forest model trained on runs kind of as it goes. And there's all this other stuff in the literature. I don't need to say SMAC is the best solution to every problem out there, but it has been a really robust algorithm over the last kind of decade and a half. I think it's arguably the state of the art in these heuristic methods. Here, I just want to say algorithm configuration has been used in many, many applications by our group, by other groups, to win algorithm competitions in real deployments. And it just really works well in cases where it's important to repeatedly solve problems of the same kind. So if you kind of understand the domain that you're in and you want to get better at it, algorithm configuration is a good way to go. One example of something that I worked on myself was the FCC, which is a branch of the US government, held an auction to repurpose radio spectrum in the United States, which ended up bringing in $20 billion to the US government. there's a kind of repeated graph coloring problem that has to be solved within the operation of this auction tens of thousands of times as the single auction happens. And all of these graph coloring problems are based on subsets of the TV stations that are participating in the auction, which we knew about in advance. So we were able to gather data that was combinatorially representative of the data we would actually encounter, and use algorithm configuration to build a special purpose algorithm just for this auction. And post hoc analysis that was published in PNAS actually showed that this led to billions of dollars simultaneously in welfare gains and in reductions in government spending compared to the algorithmic approaches that were being pursued before we got started. So algorithm configuration, I think, is really high value thing when optimization outcomes are important. So that's what I want to say about algorithm configuration generally, to kind of whet your appetite and give you the sense that this is something we should still care about. Now I want to tell you about a more recent branch of work, all of which is more recent than the stuff that I just cited, that asks about getting theoretical guarantees for the quality of configuration. So I told you that SMAC maintains an incumbent configuration. It's the one that looks the best so far. And it has this kind of core logic that I really just loosely gestured at, that as one of the SMAC authors, I'm allowed to impugn it. And I will say it is sort of like what you would do if you were trying to do a statistical test, but like somebody told you in a bar what a statistical test was, and then you sort of did kind of that. And in a sense, this leads SMAC to be very aggressive in ways that cause it to perform well in practice. And in part, this is just a bad idea. So it aggressively discards non-incumbent configurations if they don't quickly outperform, which could be good or could be bad. And it never stops running the incumbent, even when there's nothing further to be learned about it, which is just done. But it really has a strong, robust performance in practice. So as much as I can impugn it theoretically, it's pretty hard to beat, as it turns out. So, but recognizing these weaknesses in it led me to feel like I really wanted to understand what it would look like to more theoretically found algorithm configuration, to really better understand deeper statistical foundations for it. And to do that, we would need to start by asking what kinds of guarantees we would want to make about the returned configuration. So maybe the most natural starting point is I might want to say, I would like to return a configuration whose average runtime is within epsilon of the best. And for the moment, let's just imagine that I've got a fixed set of instances that I'm doing kind of a racing scenario. I've just got some fixed set of different algorithms that I want to care about. The first problem I might have is that runtimes can be unbounded. And so even in this simple setting, the average runtime could be infinite. And so I must not want quite that. So I have to make my definition a little bit more complicated. All of this can be formalized. I'm being sort of semi-formal here, but I can say that the capped runtime is within epsilon of that of the best. And whatever capping threshold I set doesn't affect too many instances. It only affects some small number of instances, which I'm going to parameterize by beta. Well, that's pretty good. But what if my configuration space is so big that I can't look at everything? It's huge or it's unbounded. Well, then I can add a third parameter. So I've got epsilon and beta already, and I can add gamma, where I say I've sampled enough configurations from my space that I can guarantee that the probability of sampling anything better than I've seen so far is no greater than gamma. So if I have so this is a definition that actually makes sense. And if I have an algorithm that does this, then I'm going to call it epsilon, beta, gamma optimal. Yeah. So this is meant to be under whatever distribution it is that I'm running the algorithm on. So, but this is only defined with reference to a distribution. So, I'm suppressing to keep from hitting you with too much notation. I'm suppressing what the configuration space is. I'm suppressing the distribution. I'm suppressing sampling random seeds from the algorithm. But I need all of that stuff too. Good point. So one of the things we did in the first paper we wrote on this was to give a lower bound theorem, to say, just based on an information theoretic argument, not looking at any actual algorithms, we can say something about how much runtime you're going to need to certify optimality at all. So don't worry too much about this. And anyway, like the actual equation is messy, so I just wrote log term. There's going to be a function that depends on the optimal runtime, the epsilon and beta, and on gamma, that is going to tell me that the very least amount of time that in principle you could spend to certify this kind of optimality. And so then there was a whole string of work between 2017 and 2023 that has offered these kinds of optimality guarantees. Mostly a sort of back and forth between our group at UBC and a group in Alberta led by Chabas Chavari. And then kind of we merged together as a super group, and then a European group came in with AC band more recently. I'm not going to go into the nuts and bolts of all of these. They're all subtly different, but they all guarantee nearly optimal performance in the sense that I just showed, and in the sense that they degrade that bound by no more than a log factor. So they nearly match that information theoretic bound. And if you look at how they work, they're all really disappointing. Because they're all completely impractical. You can't use them on anything reasonable, which makes me very sad because I really wanted this to work. But this is not what you're going to want. And the reason is this thing about the average. So the problem with average runtime is if I've got some algorithm that looks great every time I run it, I still have to be worried that the next time I run it, it might not be great. It might take 6 days to run. Even if I've got something that takes a millisecond, a millisecond, a millisecond, it could be the next thing I run it on, it's going to take 6 days. And when I average those together, the 6-day term is going to dominate. And so I have to just keep going over and over again, pounding these algorithm runs, in the face of all evidence to rule out weird tail events. And really, provably, that's what you have to do if this is your objective function. It's not like a failure of these methods, but it just leads these things to do inordinate numbers of runs and not to be very practical. So this led me to be really interested in the question of, if this is like provably the right thing to do for the objective function of average runtime, one interpretation is that was really never the right objective function. And so this led me to try to ask, what then should our objective function be? If average runtime leads to behavior that just isn't useful, then that must be a way of kind of eliciting that was never my objective function in the first place. So what then should it be? And to help you to think about that, here's a little sort of thought experiment. So consider a family of algorithms like the ones we've been talking about, mixed integer programming solvers or SAT solvers. They always return the right answer, but they vary in their runtimes. So one of them solves 99 instances in 1 second. You run the 100th instance for 10 days and it doesn't solve. Algorithm A2 runs all 100 instances for 10 days and doesn't solve any of them. I feel like most of us would prefer algorithm A1 to algorithm A2. I know I would. This isn't a trick question. I'm not going to embarrass you for having preferred A1 to A2. But notice that in terms of average runtimes, we don't have any basis for liking A1 better than A2, because the average runtimes are completely unconstrained by what I've told you. It might be that A2 solves everything in 11 days, and A1 takes 1,000,000 years on the 100th instance, and it has a larger average. And so if you really cared about average, you would say, haha, you haven't told me enough to know. But if you're like an actual human being in the world, you would look at this and say, A1 is clearly better than A2. So to me, this is a sort of diagnostic example to point out that we must not really care about average. And just to make the same point in another way, now imagine that both algorithms contain a bug and the long runs never terminate at all. Then both averages are infinite. In that case, should I feel like they're equivalent to each other because they have the same average? Again, it doesn't seem like it. So this sort of illustrates that capped runs are kind of a canary in the coal mine for thinking about our objective function. We often seem to prefer one algorithm to another algorithm, even when we've only seen part of their CDF. So we've truncated their CDFs at some point, which is what capping does. And so we need to have some objective function that allows us to reason about this sort of partial censored information. So how should we do it? People in the literature have done a bunch of things. One thing is they talk about the fraction of problems solved, which we're going to end up arguing is a sound thing to do, but it depends enormously on the parameter you've chosen of how long you let them run when you compute this fraction. They consider capped runs to have completed at the timeout, which is very optimistic. It gives you credit for things that you didn't really do. Or they consider capped runs to have completed at some multiple of the timeout. That's what Frank and I did in our early work with this par objective function, which is kind of ridiculous because it again depends on this sort of random parameter, but it was sort of a noble effort to grapple with this problem. And all of these things tend to lead to instability about the choice of some kind of hyperparameter. So all of this had us really scratching our heads really for years. We ended up going back to decision theory and kind of game theory basics and sort of axiomatizing what we understood about our preferences in this space and building up what the objective function is allowed to be from first principles. So really saying, what are some properties that my preferences over two algorithms would have to have? I'm going to... Algorithms are randomized things, and decision theory is perfect for this. It talks about randomized lotteries that produce outcomes. And so we were able to use the sort of von Neumann-Morgenstern foundations and then add a little bit of secret sauce on top and argue that there need to be essentially utility functions over algorithm runs. So if your preferences are as described in our I think there's no citation here. Oh, I guess there is. Yeah, in our 2023, I think ICML paper, then you must have a utility function that defines your preferences over algorithm runs, whether you know it or not. And essentially that's what I'm appealing to in the thought experiment that I just gave you. So let me give you some examples of how these utility functions would work. What the theory tells us is just that they live on bounded intervals. So without loss of generality, I can say the best utility you can get is 1 and the worst utility you can get is 0 because they don't care about scaling. You get a utility of 1 for an algorithm run that terminates immediately, and you get a utility of 0 for an algorithm run that never terminates, and they monotonically fall with the runtime of the algorithm. But then any monotone utility function could describe preferences that you might have. And so it's then on you as the analyst to decide which utility function describes the preferences that you have. So let me talk about some different utility functions that you might have. So one thing you might feel is I've got a linear value for money. I pay for cloud compute. I don't face an explicit runtime cap, but I have to buy my compute from Amazon EC2. So here, in order for this to make decision theoretic sense, I have to say that solving the problem is worth some finite amount to me. It's not worth an infinite amount of money to me to solve my problem. At some point, I would walk away. Each hour of compute costs some amount of money. Of course, I could go negative by spending really enormous amounts of compute, but that would be stupid because I can stop at some point. So I can compute V divided by alpha as the point where I should just stop running EC2 and just cut my losses. And this induces a linear utility function that kind of interpolates as shown here. Another thing I could do is to say, let's say I don't know what the cap time is going to be, but I have some probability distribution that describes when my client is going to tell me they need an answer by. So I'm going to run my algorithm. At some point, if it has an answer in time, I'm going to use it. And if somebody says I really need the answer now and I still don't have it, then I'm out of luck and I have to do whatever else I would do instead. So this is going to induce a utility function that looks like the probability that my runtime is less than the cap time under the cap time distribution. Of course, maybe I don't really know what the cap time distribution is going to be. So maybe I have a distribution over cap times that I only know something about, but I don't know specifically what it's going to be. Here it makes sense to appeal to the principle of maximum entropy that says among a set of distributions, it's best to use the maximum entropy one, to assume the maximum entropy one because it's the least informative. So for example, if I have if I know my distribution has support on the bounded interval, the maximum entropy choice is to say it's uniform on that interval because it introduces the fewest extraneous assumptions about my distribution. So for example, if I say my client is going to need a solution to their SAT problem sometime in the next 24 hours, and after that I know it's not going to work out, then my maximum entropy distribution would be a linear utility function that goes to 0 in 24 hours. Or I might say something like, I don't know how long the client is going to give me to solve their problem, but I know the expected value is going to be 24 hours, but maybe it'll be longer, maybe it'll be shorter. Here, the maximum entropy distribution is an exponential. So in this way, I can reason about my preferences and come up with appropriate utility functions under various assumptions that you might have. So that's everything I want to say about why we should have utility functions and where they should come from. That's something we can think about a little bit more. But here's I just want to sort of leave you with that idea that if you're reasoning about an algorithm, it really matters what objective function you pick. This average runtime objective that we often use when we're analyzing algorithms is kind of intuitively appealing, but it really leads us down the wrong path. And so really, if you take nothing else away from this talk, take away the idea that it really makes sense in a fundamental, like mathematically founded way to think about utility functions instead, and that really changes the game. So the rest of this talk is going to try to add meat on the bone to the claim that this really changes the game. So it turns out that optimizing utility, these are both optimization problems. Why does it matter? It turns out it's a really fundamentally different optimization problem. So here I'm trying to solve a maximization objective where utility decreases with time. And that means that most utility comes from short runs. If I have and that means that as I'm running something over time, I have non-trivial bounds on utility that I get for free, right? If I run something for a day and it hasn't solved yet, I know that its runtime is going to be at least a day. And that means that the maximum utility still on the table is the utility for when it terminates at a day. And because it's a decreasing function, that's probably already something pretty small. So my upper and lower bounds are going to be really close to each other, even though I haven't solved. In contrast, if I'm optimizing average runtime, after a day, if it hasn't solved, it probably matters quite a lot to the solution. And it's going to matter, furthermore, 10 times as much if it's 10 days than if it's 1 day. And so this ability to kind of bound and discard expensive to obtain tail events is a really different thing about how the algorithm works. And it's a nice thing that it not only is it algorithmically convenient, but it better reflects the preferences that we really have. So this is going to require us to come up with new search algorithms, but they're going to be easier and they're going to work better. Carola.
Yeah, just a comment. I think when we do algorithm configuration, what we have observed previously is that when we care about short-term performance and not only look at final performance, we do get much better configurations as well. So in a sense, it's similar. And I'm curious to see, I mean, we can discuss later, but whether this is really new algorithms or whether we just could also get better results for the classical algorithm configuration setting by using such type of algorithms that take into account short-term rewards, let's say.
That's a perfect setup for the next thing I want to show you. So let me tell you what I mean by new algorithms. Here's the algorithm that I'm going to advocate for using. So this is an algorithm we call optimistic utilitarian procrastination. And here's how it works. So I'm going to kind of walk you through the pseudocode because like everything else I say in this talk is going to be about variants of this. So I'm going to have a cap time. So first of all, let me think about the case where I have a fixed set of configurations that I'm racing against each other. I'm sort of running a SAT competition or something among a fixed set of algorithms. I'm going to initialize a cap time for each algorithm. I'm going to start with 1. And this is in units that you get to specify. So think of this as the very fastest runtime that it's possible for you to reliably measure, like, a millisecond or something. So really, really fast run. Just for mathematical convenience, I'm just going to put this in integer units. And I'm going to initialize this variable kappa c per configuration to be what its cap time is. And everybody's going to start out with the very smallest cap time. Then I'm also, for every configuration, going to maintain upper and lower bounds on the utility that I get on expectation from running that configuration. And I'm going to initialize these to the trivial values, which are no worse than 0 and no better than 1. So that's just uninformative upper and lower bounds. And then I'm going to have an anytime algorithm that is just going to keep running and improving until you interrupt it. And the way it's going to work is it's going to select some configuration which has the highest upper bound. So at the beginning, that's any configuration at all, because they all have an upper bound of 1. And gradually over time, these upper bounds will change. So I'm going to select some configuration, and I'm going to run that configuration on some new instance. And having done that run, I'm then going to update these upper and lower bounds. So I'm then going to use concentration inequalities you can think for now of Hufting's bounds, having observed utility. Utility is a variable bounded on 0, 1, so I can use Hufting. And I can get tighter and tighter upper and lower bounds as I make these observations. So I could just kind of do this. But if I did this, then I would be running everybody with a cap time of a millisecond. And it might well be that none of my algorithms ever solve anything within a millisecond. In fact, I kind of want that. I want to start with a cap time that's so small that it's too small. And so I'm going to have to increase cap times at some point. But before I do that, I'm going to hear what Frank has to say.
Yeah, just kappa star. What's kappa star? Initialize.
I might have just said that by mistake. Where's kappa star? Oh, yeah, sorry. I meant to say kappa.
That's kappa C.
Oh, sorry. What that's meant to, yeah, kappa sub C star is what it should say.
Okay, and what's a star?
Sorry, I'm just here trying to say, I've been using C as an index. So here I want to say C star is the particular thing that I pick that solves the argmax. So I just want to say, like, I'm going to run C star with the cap time that you would think that I would run it with, the one that is associated with it. So at some point, I'm going to need to increase these cap times. If I do it too quickly, I'm going to miss the possibility of finding good stuff that I could have found very cheaply. And if I do it too slowly, I'm just going to run on cap times that are impossible forever. So there's kind of a balancing act here. I'll tell you what it is in a second, but I'm going to have some doubling condition that's going to say, if some doubling condition is met that has to do with C, then I'm going to double C's cap time. And then every time I double the cap time, I'm going to rerun everything capped from that configuration to kind of catch it up with its doubling condition. And at the end, when you interrupt it, it has to return you an answer. I'm going to return that some configuration that has the largest lower bound. So I haven't used the lower bounds until now. I've just been talking about the upper bounds, but the lower bounds are what's going to determine the incumbent that gets returned to you at the end. So let's talk through some of these details. So this doubling condition is technical, and I'm not going to give you all of the details of it. But I can tell you that the gap between, if I think about the distance between the upper and lower confidence bounds, it decomposes into two terms that I'll call GC and GU that depend respectively only on the data that was capped and on the data that was uncapped. And I can look at the amount of uncertainty I have about this configuration's utility, the gap between my upper and lower bounds, and ask how much of this has to do with the fact that I haven't done enough samples at this cap time, and how much of it has to do with the fact that I'm capped. And at the point where GC, the part of this gap that has to do with capping, exceeds GU, that's when I double, when most of my uncertainty is due to capping. So I'm going to gather information until I reduce my uncertainty from sampling, and then I'm going to double when it comes to capping. Secondly, when I do this bound updating, I told you I could use Hufting. We actually do something better. How many of you have ever used a Hufting bound in an algorithm that you used empirically for something? Not a big not a big occupation amongst all of you. Well, those of you should come talk to me afterwards, because it turns out there's something else you can do that doesn't even really have a name. People call it a Chernoff bound, but it isn't the thing people normally mean by a Chernoff bound, where you numerically solve the equation that goes into the derivation of hefting, and it's asymptotically faster, but it doesn't have a closed form solution. And it works much, much better at the tails. So when all of your algorithms are capping, it takes only a linear number of samples to tighten the bound rather than a quadratic number of samples. So it's a really big deal in practice. It's just kind of messy to deal with, and it doesn't have a good name, but it's very cool. And it's mentioned in the Lattimore and Shivari Bandits book. But they even only mention it in an exercise. It's really hard to dig out. Okay, so what can I say about this OOP algorithm? Those of you who know about the upper confidence bound algorithm, UCB, will recognize that OOP is an instance of UCB. And so that means we get a bunch of theoretical properties out of UCB. With high probability, the returned configuration has expected utility within an additive epsilon of optimal, where epsilon is the gap between the biggest upper bound across all configurations and the biggest lower bound among all configurations. They don't have to be the same configuration. So this is the epsilon that it can prove something about when it returns a configuration at any time. And because these bounds are tightening as we run, the epsilon that it's proving is just getting better as it runs. There's a formal sense in which UCB takes no more samples than are necessary in the worst case, and it performs better on easier inputs than on hard inputs because it can bound more strongly. OOP's running time is efficient. This is something we proved specifically for the algorithm configuration case. Let me just finish the sentence. OOP's running time is efficient in the sense that if I knew what the optimal configuration was and I just wanted to certify it to somebody, I wouldn't have to do the same kind of search. I would know exactly what its runtime CDF was, and I could construct a bunch of tests based on all this information that I had. And OOP uses no more than approximately twice the runtime that it would take to do that certification. Carola, you had a question? I don't want to get into it, or I won't get to the more interesting stuff, but just there are distributions for which if you find something good and you can use it to bound other things, then it converges more quickly. Don't worry about it. We can talk about it afterwards. There's some things we can do to improve performance. So one you might notice that the upper confidence bound algorithm is designed to minimize regret, but we don't actually care about regret. What we care about here is just finding the best configuration and then using it forever, which is what Bandits people call the best arm identification problem. And it turns out there's a better version of the upper confidence bound algorithm called, crazily enough, the lower upper confidence bound algorithm, or LUCB, which has provably better performance in a certain sense for UCB and much better empirical performance when we want to do best arm identification. So we can update our code to do this. Here's the old version, and here's what we have to change to do LUCB. Basically, LUCB selects two configurations in every round instead of one. The first one is the one with the best average utility, and the second one is the one with the best upper confidence bound that isn't the one that the first one that it picked in the case where the first one had the best upper confidence bound. So it checks both the thing with the best upper confidence bound and something with really high expected utility. And then it updates bounds on both of them. So we do that. Finally, I want to get to a case where I'm not just racing in a fixed configuration space, but I'm really able to sample from a general space. So this is what we call continuous optimization, utilitarian procrastination. So it becomes COOP. So here's the OOP algorithm, and here's what we have to change to get to this continuous setting. We initialize our set of configurations now to some small initial set, and then we have a condition for sampling a new configuration, which I'm calling the add configuration, that's sort of like our doubling condition. And the way this works is we look at the gap between the upper bound and 1, and we say this is the amount of sort of money left on the table by not having sampled more configurations, right? I know the best utility possible is 1, And so if everything I'm finding is getting poor utility, then I'm interested in going out and finding new things. And I compare that potential gain to the potential gain from bringing the bounds close together. And so when I start out, I don't know anything about anything. So the first term is small and the second term is big. But as I start to learn about the configurations that I've got, I start to become interested in sampling new configurations. So that's what COOP does. And that's pretty much COOP, except for one thing that I'll tell you on 2 slides from now. But pretty much this is the COOP algorithm that I'm advocating for today. So I can now define epsilon gamma optimality. Basically, we can get rid of the beta that we had before, which was this sort of tail bounding to do with capping. That was something we had to do to deal with infinite runtimes, but now we don't have to deal with that problem because of using utility functions. And so this is a configuration that is within an additive epsilon bound of optimal in terms of utility. After we've excluded the top gamma fraction of configurations, or another way of saying it is it's provably in the top gamma quantile of all utilities. That's the same statement. And we can prove that COOP returns such a optimal configuration with no more than a specified failure probability for a given for an epsilon that is the difference between these 2 bounds, and a gamma that has to do with the number of samples that I've taken and the failure probability. These both shrink towards 0 as COOP runs, and we have this same sort of approximately efficient claim that within a log factor of the optimal thing, COOP is doing the sort of minimal amount of computation that it takes to achieve this bound. So the last thing I want to say about COOP is that we can incorporate a prediction model into it in just the same way that SMAC did, which is part of why I wanted to tell you about how SMAC works. So you'll notice in COOP that it has a sampling step that says sample a configuration at random. We need these samples to be at random in order for our theoretical guarantees about gamma to work. But if I make half of them sampled randomly, then I lose just a factor of 2 in my gamma. And I can sample the other half any way I want and just not think about it in the theoretical guarantees. And so we can take that other half and we can sample them in the way that SMAC does using a predictive model. And so we do that. Frank wrote crazy code, I think originally in MATLAB, to build these random forests. But in the modern world, one should use XGBoost from Python. Or maybe Frank is going to say he has some better way of using PFNs or something now. But we use XGBoost. And configurations sampled from the model were consistently much stronger than configurations uniformly sampled. So it really does work. This is just showing blue samples taken uniformly at random over time and orange samples taken from the model. And when we validate them, they are indeed much better in terms of utility. So this really does succeed in drilling in. Yeah, Frank has something to say.
Yeah, not about PFNs, but So it sounds like, well, empirically that this works. I can clearly see that using a model will help. I'm wondering, so for the theory, it still works because, well, it's sort of just 2 times slower, but would there be a possibility for actually making the theory also stronger by, for example, using Gaussian processes and GPUCB, which actually has better convergence guarantees than just random sampling?
I don't know. Good question. The theoretical guarantees are all worst case, so I'd be inclined to think you're going to have to change from a worst case guarantee to something else. There might be a way of doing something else. Really, the way I think about it is that I think SMAC did exactly the right thing when it comes to sampling. I think sampling a bit at random and a bit from a model was a great idea. I think random forests worked really nicely because they don't extrapolate. They can deal with discontinuities really nicely. I feel like that part of SMAC's design was really great. But I think what SMAC did badly was the sort of statistical evaluation of the set of samples that it's got. It didn't really reason very sensibly about when to discard things and when to stop learning about things. And so I think this is putting those 2 pieces together in a different way.
I am just wondering, like the theory behind SMAC was never, well, I never did any, but GPUCB actually, well, there's all these convergence guarantees in Bayesian optimization for expected improvement and for UCB. And I'm wondering whether those two
Yeah, I
theories
mean,
play
I
together
don't
or
see
not.
why you couldn't bootstrap some of that stuff together. It's not work that I'm familiar with, but I'd be happy to learn more from you or from anyone
Yeah,
else here who works on
it's
that.
also not me, but there's some people in the room who
Yeah,
know
that'd
that.
be cool. Okay, well, I've got just a few minutes left. I want to tell you about what kept me up late at night, which is we've been trying to do empirical evaluation of all of this to really try to make the case that what I claimed about the old theoretically motivated algorithms, that they just sadly don't work in practice, is not true about COOP. COOP, I want to claim, really seems like it actually is the thing that you should use in practice today. So the first, and I should say that this experimental work is really preliminary. It's almost all unpublished. It's still kind of actively going. So this is the first time I'm talking about it publicly, and this is we're going to have to add yet more detail to this before we're ready to publish it. But we're at the point now where I wanted to come to this audience and tell you about this because I now think I've seen enough to believe that it's true. So. So the first thing I can do is compare to other procedures that offer guarantees because people want to see baselines. Here I'm showing the runtime over time of a bunch of different procedures that offer guarantees. The x-axis is the amount of time spent. The y-axis is the percent gap to optimal. So this is in a set of discrete configurations where we know the value of every configuration because we just paid the cost of validating them. On 3 different problems, I think from AC-lib, and using a log Laplace utility function, which I think is a sensible utility function that says your utility sort of falls geometrically with time. And some of these algorithms are anytime, which means they would return an answer at any point. Some of them are not, which means you just run them with some parameters. They take an amount of time that is sort of unknown to you. And then at some point they give you an answer and they stop and they can't really be continued. So for those latter ones, I'm showing scatter plot points. And for COOP and OOP, I'm showing curves. These are all validation data, not training data curves. What you can see is that COOP, so COOP here is running on a discrete set. But notice you can still run COOP on a discrete set. So it's still going to start with a subset of that discrete set, and then it's going to add new configurations as they come in. And sometimes that's better, and sometimes it's worse. We've tended to find that COOP actually is faster on average anyway, because it can start learning about some of the configurations and using them to bound other ones. And so it depends on the distribution, but often it's better, even though it's sort of targeting this continuous setting. And the big takeaway here is that successive halving, hyperband, and AC band, which are the only things we know about that offer theoretical guarantees and can be run on arbitrary objective functions, are all pretty healthily dominated by COOP and OOP. Cplex RCW is the case we've seen that looks the worst for us, which is why I'm showing it here. Here, some of the hyperband values were better. But even so, hyperband is not anytime, and so you have to sort of magically guess parameters that are going to get you in the right part of the space. So overall, we thought this looked pretty good in terms of comparing to people who offer guarantees. There are other algorithms. No, I think this is an average over 10 runs, and that's where the error bars are coming from. So you can see many samples of the same color for hyperband and AC. That's why we're showing error bars on all these plots. That's because it's validation performance, not test performance. It's validation in terms of what it believes, but it's not necessarily, sorry, it's monotone in terms of what it believes, but sometimes it'll change to a new incumbent that's worse. So that's what we're seeing. Like, asymptotically it gets better, right? But sometimes it'll like instantaneously like somebody who's not better. Yeah, I mean, notice this is on a log scale, so that non-monotonicity is happening sort of, under 20 seconds, kind of like just in the early days. Here we're comparing to the theoretically grounded algorithms that I showed you before that are only able to optimize runtime. They're really based on these runtime assumptions very fundamentally. Here we use a linear utility function, sort of average capped runtime, sort of par 1. Which is the closest we can get to a fair playing field for these algorithms that can only think about runtime. And here you see it's really not close if we compare to all of these previous things. They're really a lot worse. I guess, and here we include AC band as well, even though it works with arbitrary utility functions, because there are some senses in which it targets runtime optimization. And so we weren't sure if it was a fair comparison in the previous plot. But again, against these baselines, I think it's not especially close. And I should say we have not yet been able to rerun these with all of our optimizations. So these are not using models. These are not using our fancy Chernoff bound. This is just using Hufting bounds. And this is not using LUCB. This is just using regular UCB. So we think this would all the Coop results would be a bit stronger with those modifications in. Then we have been comparing Coop to SMAC on AC lib scenarios, which is easy to say but hard to do. So we've now SMAC. At least in principle, you can go in and change the code so that it can optimize any objective function. And we've done that so that we're doing kind of utilitarian SMAC on arbitrary utility functions. We ran these experiments on a log linear utility function here. So notice that the utility function looks linear, but it's on a log scale. So it's saying every doubling of runtime decreases your utility by a half. So we looked at 80 AC lib scenarios, 20 distributions, and 4 solvers. And basically what we found is that we had almost the same performance across the board, both in time and like over time and in the final solutions. So after 4 days of wall clock time, here's the CDF of the Coop utility minus the SMAC utility. And you see almost everything was sort of within epsilon of each other. So almost all of them are finding the same configuration or qualitatively same configurations. I mean, these are like based on actual runs, so they're not literally the same configurations, but they're getting the same utility. And then there's a bit of a tail on both sides where SMAC is maybe a little bit favored in the tail, but it's a pretty small tail on both sides. So this is in terms of their validation performance of the thing that they returned. But of course, the big difference between SMAC and Coop is that Coop also offers optimality guarantees. So for these 80 runs, these are the anytime optimality guarantees that Coop is also outputting, saying what epsilon it is proven and what gamma it's proven about the space that it's searching within. And so you see that we were tending to get down to epsilons of about 0.1 and getting the gammas were sort of varying, but gammas of about 0.2 or 0.5, somewhere between 0.2 and 0.5. Depending on the scenario. So broadly speaking, what we've seen in these results and in other ones that aren't polished enough to show you is that we're roughly matching or sometimes exceeding SMAC, but also with theoretical guarantees kind of thrown in for free. Something we've kind of found is that utilitarian algorithm configuration is just easy more often than runtime configuration is. Once you prove that you found an incumbent that gets high utility, once you find something with utility of 0.98, there's not much point in continuing to run. You get the epsilon small. There's not much else that you could hope to find. It wouldn't give you very much. And that's what we're sort of starting to find when we go across a lot of scenarios, that for the given utility function we pick, they're just both finding something pretty good. And then there's just not much searching left to be done. This led us to think a bit about what makes a data set hard. If I wanted to try to make a data set that was as hard as possible, what would it have to look like? And our intuition about average runtime is that it's going to be dominated by long runs. And as I told you before, even when an incumbent is consistently good, I'm going to be hunting around for runs that rule out the possibility of long runs. But average utility is dominated by short runs. So long runs yield very low utility, so they don't matter very much. So good algorithms don't actually do long runs almost at all. They're looking for short runs. So the hardest scenarios are going to be needles in haystacks, where they're very rare configurations that are very much faster. And so they yield measurably higher utility, but they're so rare that you have to do a lot of searching to find them. So to try to set up a scenario that was going to be as hard as possible, we constructed a synthetic scenario that has these properties. So here's a synthetic hard scenario that sort of gives this needle in a haystack property. So we have a utility function that looks like a reciprocal that says the amount of time divided by the number of seconds is my utility. And then we have a runtime distribution that's exponential. So about half of my configurations have a runtime of 2,000 seconds, and then a quarter have a runtime of 1,000, and then an eighth have a runtime of 500, all the way down to 1 over 4,000 having a runtime of 1, and 2 over 4,000 having a runtime of 2, and so on. But look at the utility numbers. The utilities are really, really small on these common scenarios, and they only spike up to 1 at the very end. And so getting high utility is going to involve doing lots of sampling to find these really rare needles. And we simulated this. So the nice thing about this is that I don't actually have to have these be the times. I can just lie to the wrapper and say that this was the runtime. So we can do these experiments with SMAC and COOP. And here we see that COOP really is performing consistently better than SMAC on scenarios like this. In fact, so much so that my students didn't keep running SMAC to the point where it was getting a utility of more than 0.6, because just the overhead of all this model building, even so, was making this an expensive experiment to run. But you see COOP within sort of 10 to the 7 seconds here is saturating to a utility of 1, and SMAC is still kind of dribbling out at a utility of 0.6. And generally what we found is that SMAC tends to get stuck on mediocre incumbents. So SMAC has a hard time switching once it's learned about something that's good, because it very aggressively rejects things. So if good things come along very rarely, COOP is going to study them once it gets them, but SMAC is going to rule them out a little bit too aggressively and really have trouble finding them. I'm almost done. I'm eating into our coffee break slightly, but I have one last thing I want to tell you quickly, because I think it. Let me just take the question at the end, because I'm going over here. But I want to tell you this last thing because it's easy to say, and it's a nice sort of cap to the story. It's probably occurred to you that you might not know exactly what utility function you want to pick. And in part, I'm going to tell you, kind of too bad for you. Like decision theory is hard. You have to decide what you want if you want to go out and use a computer to get it for you. So, AutoML is all about automating the process of building something, and without the right objective function, you're going to do the wrong thing. But I can say a little bit more than that kind of tough love message. I can say that we can do this sort of counterfactual utilitarian analysis for free based on the information that we gather through a single COOP run that allows us to think about the robustness of the utility function choice that we made. So let me define the regret of a solver as the expected utility of the best solver under whatever utility function I'm talking about versus the utility of the solver that I'm speaking of, S. And so given the data that I've collected by running COOP with a given utility function, I can characterize regret for a bunch of different utility function parameters, and then sort of say counterfactually, if the parameters had been different, here's what I would have liked better instead. And to make this argument, this is my last slide, I promise, we took the SAT competition as an example of a case where a bunch of interesting algorithms are being raced against each other. We ran COOP on them with the objective function that the SAT competition used, and then we asked, what if they had changed their parameters? So the SAT competition ranks solvers using a par2 utility function. Whether you think that's sensible or not, at least it can be expressed as a utility function. So we did, and they have the timeout as 5,000 seconds. So they say, we're going to average your runtime up to 5,000 seconds, and then if you time out, it's going to cost you 10,000 seconds. That's interpretable as a utility function. So we can compute these regrets according to the par2 utility function, and then we can say for every value that the timeout could have been, other than 5,000, everything up to 5,000, I can look at the CDFs that I gathered anyway and say what would have happened, what regret would I have experienced if that had been my utility function. And doing that, I can look at the sort of lower envelope of these regrets. Whatever lies in the lower envelope is the thing that I would have preferred, the zero regret algorithm at that utility function, and just plotted, here I'm just showing you kind of that level set. So what we can say is that the thing that won the SAT competition would have also won for cap times down to about 1,000 seconds. But then below that, actually the fourth ranked solver was best for almost all timeouts below that. So this is, first of all, maybe an interesting thing to know, particularly if you're the person who made KISSAT mab prop no sim. But also kind of interesting, just sort of as a case study about how you might do an analysis that isn't tied specifically to one utility function. So I'll leave it there. So I've argued that algorithm configuration is AutoML in the design space of algorithms. No, I don't think large language models are going to make algorithm configuration obsolete because you really need to do this kind of careful experimental design and validation. I don't think that's going to go away by asking a model what it thinks about my algorithm. I do think LLMs might yield a very interesting proposal distribution for new configurations, which could be folded in much the same way that we're using the sort of SMAC model now. To date, the most practical algorithm configuration techniques have been heuristics like SMAC. There's been a growing body of work over the last decade on how to do theoretically grounded algorithm configuration. And this talk has tried to argue two things. First of all, regardless of how you do algorithm configuration, you really should be using a utilitarian objective. Secondly, utilitarian algorithm configuration is actually easier, so you'll be happy once you make the switch. Particularly when it comes to proving theoretical guarantees, also when it comes to terminating and just saying that you're ready to be done. And this particular algorithm that we've advanced called COOP is, I think, the one that you should be trying now. It's fast when SMAC is also fast. It's faster than SMAC in hard cases, and you get clean guarantees for free. And if you're not sure what utility function parameters to use, at least sometimes you can do a counterfactual analysis and understand something about the robustness of your choices. So I'll leave it there. Thank you for your attention, and thanks for the invitation.